Check it out now, y'all.
nanoHUB-U, online instruction.
Hello, welcome to Lecture 4 on Thermoelectric Systems. Today we are going to talk about graded materials and the effect of the thermoelectric leg geometry. Maybe some surprising result that you can see how we can enhance or improve the thermoelectric performance beyond the material properties. Something that we saw before is that in a thermoelectric material you have typically N and P legs that connect that are between a hot and a cold side. And we also learned that Z times T is the figure of merit, and you always want to get a high Z times T. The question is, whenever the temperature difference between the hot and the cold side is large, it's hard to get a material that has highest Z times T in the whole temperature range. This is a graph showing for a standard commercial bismuth telluride, lead telluride, and silicon germanium material, where the optimum Z times T resides at different temperatures. This is near room temperature, near 500 Kelvin, or 1000 degree Kelvin. So the question is, if we have to cover such a large temperature difference, often what we have to do is to combine, and this is called segmenting different legs. And the rule of thumb is at each location you want to get the highest ZT at that temperature. One thing we want to look at today is how much this local optimization of ZT give us the global optimum. There is a paper, a quite interesting paper came out in 1991 by Bergman and Levy that said a thermoelectric property of a composite material, the Z effective of the composite is always, never exceeds the largest value of the Z of any of the components. This and they have done the rigorous proof for a two-component system and the heuristic proof for general multi-component, is a very powerful statement that tells by just geometrical mixing of materials with different Seebeck electrical conductivity and thermal conductivity, we cannot improve Z times ZT of the material. But Z is a ratio of material properties, Seebeck coefficient, electrical conductivity, and thermal conductivity. Each one of them can be defined for a composite, but definition of Z for a multi-component system requires some attention that we are going to discuss today. Another relevant article is something that came out in 2003, the work of Snyder and Ursel, that introduced the thermoelectric compatibility factor. This is related to ZT, but as well as the alpha, in this case is the Seebeck coefficient, and this compatibility factor is an additional material property that needs to be taken into account when you segment different materials. Basically, when we put material A in series with material B, the same current flows through them if it's the same leg. So the optimum current operation for them should be somehow matched, and this compatibility factor take that into account. So this if you relax the idea of having the same cross-sectional area or the same leg to segment, then you don't have to worry about compatibility factor, and you can use cascaded generator. So that's another relevant paper that came out. But let's go back and see how this Z times T was established. In week 2 lectures by Professor Landstrom, you saw that in a single leg thermoelectric, when we send the currents, there is Peltier cooling and heating at the junctions and Joule heating along this in the bulk. The net cooling at the cold side is the amount of Peltier cooling minus half of the Joule heating and minus the heat conduction from the hot to the cold side. This is a quadratic equation in current. It's optimized for this value of the current and give you a delta T max, maximum cooling for a thermoelectric refrigerator, which is only a function of Z times temperature on the cold side squared divided by 2. One thing to mention is delta T max includes already a T hot minus T cold. So this equation has T cold on both sides of it. If you want to obtain T cold only as a function of T hot, this is a second order equation that you can solve. So that's something sometimes is not taken into account. But anyway, these tell you that the T cold is only a function of Z, the material properties. This is also geometry independent. When you change the size of the leg and so on, this optimum current and so changes, but the maximum cooling doesn't change. And at maximum current, half of the cooling power is cancelled by the Joule heating. So one idea is that can we go beyond that? Can we beat this 1/2 ZT square limit by redistributing Joule heating inside the material? What it means is that assume I have two legs. Each one of them has the thermoelectric coefficient. Peltier cooling or heating happens when the current enters from a metal to a thermoelectric material, but you have a distributed Joule heating inside each layer. This distributed Joule can be simplified as two localized heat sources at the two junctions, the hot and the cold junction. So you can treat a multi-element or multi-segment thermoelectric legs using the simple thermal circuit. The idea, the intuition came about of how a graded thermoelectric material could be designed to get a higher cooling came from Seebeck. And the idea is that let's take a leg of a thermoelectric with length L, Seebeck coefficient S, electrical conductivity sigma, and this corresponds to a resistance R, and thermal conductivity is also given. Now let's add a segment that is a quarter of the length with twice as high Seebeck, but 4 times as low electrical conductivity. Seebeck squared times electrical conductivity is the same as the first segment, so this material has the same ZTS here. And this is 4 times shorter. Why? Because this is 4 times more resistive. You get the same resistance. After this, you can add a leg that is 1/9 of a length of the original leg with a Seebeck coefficient 3 times as big and electrical conductivity 9 times smaller, the same resistance. The intuition of Seebeck is that at the optimum current, I equal S times T times R, Joule heating and Peltier cooling are cancelled inside the material. And with a simple resistive network, you can calculate delta T max is 1/2 ZTC square times this factor, which is the number of sections. This is actually a quite surprising result because you can see that you can get higher than 1/2 ZT square by a factor which is definitely positive. And if S max divided S mean, the ratio of these, how much you can change Seebeck without changing the power factor is 10, this could be 30 to 80%, so that could be quite substantial. This seems to contradict what we said earlier about Bergman and Levy article on composite thermoelectric. Now we have a material that is composite of 3 legs, and its delta T max beats 1/2 ZT square. And here really is the very delicate point is Z of a composite material. It doesn't really have a meaning because Z is defined as a balance between Peltier and Joule. When you redistribute the sources of cooling inside the material, you need to write the whole balance equation. So then there is not as much meaning to use the same Z as you had when everything was uniform. So that's the kind of where the previous assumption is not taken into account, and there we can benefit. Seebeck continued this work and even considered what will be a continuously graded material. Assume power factor and thermal conductivity are constant throughout the material, and assume there is a small ZT. The equation for heat balance inside the material can be written. This is the term which is the Fourier diffusion equation we saw in lectures in week 3. This is a Joule heating, which is a localized effect, but now because Seebeck coefficient changes as a function of distance, you have a Peltier effect as a source of the Fourier. And let's assume S square sigma at each location is constant. We are able to trade off between S and sigma without changing Z. The question is, what will be the maximum delta T? Again, Bian quite elegantly in this paper showed that ZT max is 1/2 ZT squared, temperature on the cold side, but in addition, you have the factor that have to do with the integral of the Seebeck coefficient square or integral of the Seebeck square. A question is, what will be the optimum profile? This is not a simple equation to calculate the optimum. This is something that in the same paper in 2007, Bian and Hongyan Wang did together. The optimum Seebeck profile for a material actually has this shape. So this is cold side, this is the hot side, this is the heat sink. What they said is that if between the values of S0 to SL, you can change the Seebeck coefficient by trading off electrical conductivity so that the power factor stays constant, the advantage is to get half of the material to be at a low Seebeck material. A section of it where the Seebeck increases quite quickly with distance, and then a small section at the end where Seebeck is to the highest value. And if you use this, the delta T max is given by this relation. Again, you can see it's bigger than 1/2 ZT square and is related by this logarithm of the Seebeck at the low side and the Seebeck at the side near the heatsink divided by the side near the cold side. This is analytical optimum under these assumptions here. That teaches us the kind of intuition of what optimizes a thermoelectric device. It's not a simple intuition. Why this shape gives you the optimum is not at all obvious in the first sight. But later on in the paper they did is that actually what gives us the optimum performance is a uniform efficiency criterion. When you have a graded material and you convert heat into electricity at each section, you have certain efficiency. And it's not actually the ZT locally that give you the conversion efficiency, because the heat currents add up as you go from one side to the other. What you need to consider is the overall efficiency and make it as distributed, as uniform as possible. A question is that this type of calculation is for toy examples. How much really in practice a non-uniform Seebeck profile could help? This is a work that Bian did later on. A conventionally functional graded thermoelectric material, one tried to optimize material ZT at each location. So here is the cold side, here is the hot side. Through an iterative algorithm, the material properties, Seebeck, electrical conductivity are modified so that we get the highest local ZT. And you apply a current. Of course, this side become cold, 240 degrees. This side is room temperature, 300 degrees. This is the temperature profile across the leg. And at this operating temperature, this is the local ZT, and you see ZT is high between 0.72 to 0.78. This is what you can do with the state-of-the-art bismuth telluride material. This is the case of local maximization of ZT. Now, if you remove that constraint and use the maximum uniform efficiency criterion, this is now the same leg thickness. This is now the ZT profile. You see most of the ZT, most of the leg is 0.7, similar to this. But near the hot side, in the 20% of the leg near the hot side, we sacrifice ZT to go down to even 0.5. The average ZT of this material is lower than this material. But using this profile, if we calculate the temperature in the device, the net cooling is significantly more. Instead of 240, is 210. So graded bismuth telluride can increase maximum cooling of TE refrigerators by about 30 degrees without changing a maximum ZT. And this really comes from the power of the grading of the material, and that's something that was neglected in the past. That's an opportunity to improve cooling performance for graded material. Let me summarize this part of the lecture. We discussed about inhomogeneous thermoelectric. It's possible to beat the limit of 1/2 ZTCS square. and cooling efficiency also can be improved. Analytical solutions are given for constant power factor approximation, and they point out the uniform efficiency criteria as the main criteria to design a graded material. And finally, we show that the cooling enhancement, of course, is independent of the dimensions, and it can be quite significant for bismuth telluride. In the next phase, now we discuss now what happened if we change the material in the leg. Now let's discuss about the geometry. How about the leg, instead of being all square, you have a tiny contact on top and a large contact in the bottom? How about if they're circular? How about this pyramid? Can the thermoelectric leg geometry improve the performance? These type of questions, of course, analytically you can approach them, but today with finite element you can almost do numerical experimentation. Here let's take a bismuth telluride material. The material property is given, Z times T is about 1. Let's take a leg that is 200 micron, 0.2 millimeter thick, and in this case 410 by 410 micron square. This is a simple square legs. And we simulate 1D geometry when the top contact is cold. Here is the heatsink, and a 3D geometry where we only use a device that is only 50 by 50 or 200 by 200, up to 200 by 200 micron with the same leg geometry. And we let finite element analysis like ANSYS give us the maximum cooling. Here are the simulated, calculated delta T versus current for this single leg. For the case of a 1D geometry, we get the maximum cooling of about 76 degrees. That's what you predict by 0.5 ZT. No surprise. But if the top electrode is not 400 by 410, is smaller, 200, 100, or 50, the maximum cooling could be even more than 100 degrees Celsius. This was presented almost 10 years ago, and at first sight seems quite surprising. Here are the actual finite element simulation results showing the grid, here showing the 1D geometry and 3D geometry, and you can see the maximum coolings are different. The question is that a numerical artifact, or is really we can increase the cooling performance by changing the geometry? This seems to be too good if we can just change the geometry and get higher cooling. There is a very nice paper by Vladimir Semeniuk, president of the Thermion Corporation, that the efficiency of cooling thermoelectric elements of arbitrary shape. In this case, he looked at cases where not only thermoelectric element, this could be pyramid, but any arbitrary shape. They solve Poisson equation because that dominates both electrical current distribution as well as temperature distribution with some assumptions, ideal kind of contacts and so on. The conclusion is that maximum energy conversion efficiency in the most general case is independent of the shape of the conductor. Basically, if this paper is true, then the previous result kind of cannot make sense. How is both of them could be valid? When one look at this more carefully, they see the boundary conditions are different. In the case of Semeniuk work, they use a uniform potential, a constant bias at an electrode. In our simulation, we use a uniform current density. It was at the time, just without current and voltages could be interchanged. We didn't pay as much attention, but this has a significant impact. These are the simulations with potential distribution and temperature distribution with a uniform potential. With a uniform potential, you apply a potential on top of a device and you let the current flow, and you get a temperature cooling of about 76 degrees. This is, again, ANSYS verify. With the same geometry, which we change the conditions to uniform current. Now the potential distribution is not the same on top of a device because you apply the same current everywhere. The potential needs to adjust, and the maximum cooling is now 91 degrees Celsius. So really the difference between the two comes not because of the geometry alone, but with the boundary condition of current versus voltage. Here is the temperature distribution across 50 micron center of the cooler. When you apply a constant voltage boundary condition, you get the cooling that you would expect. But when you apply a constant current boundary condition, the cooling has a curvature, but you have a region in the center where the cooling could be quite more than what you can achieve otherwise. Not only the cooling is more, the cooling power density could be more. So a 1D device with a thickness of 200 micron has a cooling power density of about 100 watt per centimeter square. If we keep the hot contact the same size, 400 micron, but we make this cold side only 20 by 20, the 3D device, not only the maximum cooling at this region could be more than 90 degrees, but the cooling power density could be more than 600 watt per centimeter square. How one could in practice achieve such uniform current? Of course, what we need is to adjust the voltages at each of the segments so that the current is more uniform. Here is the potential we need to apply at different segments in a 70 by 70 micron device. It should change by almost a factor of 2, but it gives us an idea how we can achieve this uniform current. Let me summarize. In part 2 of this lecture, a 3D device can cool better than the 1D under the condition of the uniform current, and you can get power densities of more than 600 watt per centimeter square and maximum cooling quite high. And a way to achieve this is by creating an array of electrodes to control the distribution of current. Overall, in today's lecture, we saw 2 cases where the material grading or the geometry of the leg is used to modify the thermoelectric device performance. They work kind of quite well for cooling. For power generation is harder. What we will do in the next lecture is that we look at now some of the tiny device effect, ballistic effects, and see how they can affect thermoelectric device performance. Look forward to see you in the next lecture.